One reason that the troop moved more slowly than expected, and in particular one reason why the group spread out, was due to statistical fluctuations and dependent events. Of course, the other reason why the troop moved more slowly than expected was because of Herbie. Herbie is the bottleneck, and if you have a group of people who need to get from point A to point B, and they all need to get from point A to point B, then the group doesn't get there until the slowest person gets there. In the hike, Herbie is the person who sort of has the least capacity for covering miles. We can think about it more generally. A bottleneck is a resource whose capacity is less than or equal to the demand that's placed on it. And another name for bottlenecks, and I use them interchangeably, is a constraint. As Jonah explains in Chapter 18 in The Goal, we can think of any system in business, and indeed most systems in life, as comprised of two types of resources, bottlenecks and non-bottlenecks. Which type of resource needs to be optimized in order to increase plant capacity? Well, by definition, if you go back and look at the definition of a bottleneck is a resource for which we don't have enough capacity. So if we can increase the capacity of the bottleneck, we can get more work through the bottleneck and give it an amount of time, we'll be better off. What's the impact of increasing capacity or reducing setup times at non-bottlenecks? If we do something to add capacity at a non-bottleneck, we make some kind of improvement in a non-bottleneck, or we figure out a way to reduce non-productive time such as setups at a bottleneck, are we going to be better off? No, we're not, because remember, by definition, we've got excess capacity at the non-bottlenecks. So we're just essentially adding excess capacity if we take those actions. Where should an organization focus its process improvement activities? On bottlenecks or non-bottlenecks? Let's kind of take a look at an exercise here on the next slide. So here we have a very simple system. We can think about this as an assembly line or some other type of production line that consists of three workstations or three work centers. We can think of this as lots of other examples in business where to get work done, the work has to pass through three different resources. Maybe it's three different offices or three different people, and those resources have to do their work in a particular sequence, and each one of those resources has a particular capacity. In our example, let's assume that market demand is 100 per day, and you can see the capacity of each resource up here at the top. But just to make things a little bit more interesting, let's say that each resource currently has a scrap rate of 10%. So for every 100 that you put into a particular work center, you only get 90 out. Let's think about what the effective capacities then are of each one of these work centers here in our example. Let's start with work center 2 because that's probably the easiest one. If we take 0.9 or 90% times its capacity of 100 per day, that gives us an effective capacity of 90 per day, not 100 per day. And if you do the same thing, if you multiply 0.9 or 90% times 115 over here for work center 1, you'll see that that's 103.5. And of course we'll get the same thing over here on work center 3. Again, multiplying 0.9 times 115. So here's our challenge. Here's our problem. As you can see down here at the bottom, it says that we can increase our overall output by investing some money in decreasing the scrap rates of these work centers. Unfortunately, we have a limited budget, and we can only afford to invest in two of the work centers. Whichever two work centers we invest in are going to have their scrap root rates reduced down to zero. So in other words, they will produce 100% good output. So which resources should be our priorities? Should we invest our money in work centers 1 and 3, work centers 1 and 2, work centers 2 and 3? And how do we make that decision? So I'd encourage you to pause the presentation and take a few minutes and think about this. So let's talk about what happens. Let's start by recognizing that the bottleneck here, the constraint in this system, is work center 2. So it's pretty clear that we want to invest our dollars in work center 2. So then our question becomes, do we do 2 and 3 or do we do 2 and 1? So let's start out with 2 and 1. So if we invest our money in work center 2, then that means for every 100 that we put into work center 2, we'll get 100 out. And since we're also investing our money in work center 1, if we put 115 into work center 1, we'd get 115 out, because remember, we've driven the scrap rate down to 0 here. But you have to ask yourself, does it make sense to put 115 in every day? Because how many can I get out? Well, I can only get out 100 because that's all I can get through the bottleneck. So if I put in more than 100 every day, they're just going to build up. I'm just going to have more and more inventory within my system. So really, I only want 100 units to hit the bottleneck every day, because that's as many as I can get out. So I want to get 100 out of work center 1 every day. Now, how many do I have to put in to get 100 out? Well, again, I've driven my scrap down to 0, so if I put 100 in, I'll get 100 out. So far I'm putting 100 in 1, getting 100 out of 1. Those 100 go into 2, and they come out of 2. Now let's look and see what happens when I take those 100 from work center 2 and put them into work center 3. I put 100 in. How many do I get out? Well, remember, I have a yield of 90%, so I only get 90 out. So in this case, even though the market will absorb 100 units per day, I'm only able to sell 90 units per day. That's all I can get out of my system. Now let's think about if we spend our money going the other way, then that would be investing in work center 2 and work center 3. Again, let's start with the bottleneck. We know we want to invest some money at the bottleneck, so let's talk about that. That's the same situation. We'll put 100 in and get 100 out. And when those 100 come out, they go into work center number 3. And again, I've invested my money now in work center 3, so I can get 100 out. Now, I got to feed 100 per day into work center 2. How do I get my 100 per day into work center 2? Well, of course, I got to get them out of work center 1. So what can I do? Well, if you take 100 and divide it by the yield, 0.90, you'll realize that you get 111. If we put 111 units in to work center 1 every day, we'll get 100 good units out. In other words, if you multiply 111 times 0.9, you'll see that that comes out to 100. So what I want to do is then I want to inspect, the units that I put into work center 1. Expect those 111 units, sort out the 11 bad ones that are in there every day, and pass the 100 good ones into work center 2, and so on. Generally, I never want to run anything that's already damaged, defective, or problematic in whatever way through work center 2, because remember, that's my bottleneck. I don't want to waste any time, any resource on my bottleneck, so I want to make sure that it's not already bad when it hits the bottleneck. So it makes sense to inspect before the bottleneck. And by definition, I've got some excess capacity here. I've got plenty of excess capacity here at work center 1 to run some extra material through, sort out the bad stuff, assuming I can do that fairly effectively, and only run good stuff then through the bottleneck. Similarly, once it's cleared the bottleneck, it's golden, right? So I don't want to waste anything that's been cleared through the bottleneck. So up here downstream from the bottleneck, I don't want to rely on inspection anymore. This is where I want to rely on improving my processes so I don't damage anything or have to scrap anything once it's been through the bottleneck. So you can see that the world starts to look a little bit different when we start to think about our businesses in terms of bottlenecks and non-bottlenecks. Traditionally, some of us might think that improvement anywhere is good, and improvement anywhere is going to add up to improvement of the whole. But you can see that that's not really the case if we've got bottlenecks in our system. What bottlenecks determine where we should spend our improvement resources, and more generally, how we should manage the system. We should manage bottlenecks differently from non-bottlenecks, and we'll talk about some of that next. Here is a process for managing systems with bottlenecks. It's a 5-step process, and it's called the 5 focusing steps. And the goal, the author doesn't use the exact terminology, the 5 focusing steps, but he has many examples of the 5 focusing steps in the book, particularly in chapters 20 through 23. The first step is to identify the constraint. The second step is to exploit, or what I like to call squeeze the constraint, squeeze everything we possibly can out of the constraint. Step 3 is subordinate other resources to the constraint. Make sure other resources are focused on supporting the constraint and squeezing all we can out of the constraint. Step 4 is elevate the constraint, which is making investments to increase the capacity of the constraint. And then step 5 recognizes the fact that we might do such a good job managing a constraint and elevating the constraint, squeezing everything we can out of it, and increasing the capacity of the constraint, that it no longer is the constraint. We've raised the capacity of it so much that now the constraint has shifted to somewhere else in our system. So let's talk about these steps, particularly the 3rd, 4th, and 5th step with respect to what happened in the goal. The first step, again, is identify the constraint, and that actually happened in the goal in a little bit earlier in the book in chapter 18. They identified the constraint by checking with expeditors to see when shortages occurred, what resources were responsible for those shortages. They looked for buildup of work in process inventory, which should make sense. A constraint is like a bottleneck in a pipeline system. Work is going to build up behind that bottleneck, waiting for its turn to get through the bottleneck. Another thing that you can do if you have good data and you understand how much of each resource it takes to produce a unit of a finished product or a unit of a finished service, then you can basically multiply through market demand for each one of your products and services and figure out what load that the market places on each one of your resources. And any resource that has a load greater to or equal in capacity would be a constraint or a bottleneck resource. In the goal, they tried to do that. It didn't work out because their data weren't very good, but I've got some associates that practice this methodology, and they find that that's often a successful way to do it if the company has good data. So that's identification. The next step is to exploit the constraint, and again, I like to think about this as squeezing everything we possibly can out of the bottleneck. So one of the first decisions they made was to only work on what's sold or what's late. In other words, if you've got limited amount of constraint resource and you've got a lot of material that's already sold, orders that are already sold, you've basically got somebody waiting to write you a check as soon as you ship that stuff. So it's better in terms of profitability, in terms of throughput, if we can build that stuff than just building inventory that's maybe going to sit on a finished goods warehouse shelf somewhere. Scheduling breaks and things around setups should make a lot of sense to you. Whenever the machine is stopped, if it's a bottleneck, we want to get that thing set up, get it going to the next job as soon as possible. It's absolutely critical to maximize utilization of the constraint to minimize idle time on the constraint. Stationing a permanent crew at the NCX-10 basically does the same thing, as does the 4th bullet point here. Anything we can do to use the constraint more efficiently. For example, loading the furnace more efficiently so you can cram more in to each load, basically. Makes sense. And we talked a little bit more earlier about making sure that we aren't running anything that's already defective at the constraint. So in the goal, they inspected parts before they hit the constraints. The next step is subordinate, and this is the step that businesses sometimes have trouble with. A couple good examples of subordinate in the goal. One is the red tag, green tag system. You may remember that the basic role in the red tag, green tag system is that this system was designed for the benefit of folks who are operating non-constraint or non-bottleneck work centers. Red tag parts are parts that are bound for a constraint at some point in their routing after they leave your work center. Green tag parts are not bound for a constraint. So the basic rule is that if you're working on a batch of green tag parts and a batch of red tag parts shows up, under a lot of circumstances, you should stop working on the red tag parts and start working on stop working on the green tag parts and start working on the red tag parts. The problem with that, or you might perceive it as a problem, is that you waste a setup, right? Because you have to break the setup on the green tag parts, set up for the red tag parts. Then when the green tag parts are done, when the red tag parts are done, set up for the green tag parts all over again. And if you're one of those operators that has to do that, that might make you feel uncomfortable. You might not be very happy about that because it decreases your output, right? It makes you less efficient, but that's okay. This principle of subordination means that we essentially suboptimize the performance of non-bottleneck resources in order to optimize the performance of bottleneck resources. So we make the non-bottlenecks quote-unquote less efficient, looked at just in isolation, in order to make the bottlenecks more efficient. Remember, by definition, we've got excess capacity at non-bottlenecks, so it's okay if we spend extra time doing work at non-bottlenecks. What we want to do, and what the non-bottleneck resources have to understand, is the most important thing is to help optimize the bottleneck. So again, we're sort of we're subordinating some performance at the non-bottlenecks to the bottlenecks. Heat treat is the same type of situation. We heat treat parts to make the parts more malleable, and that allows us to run them faster. It makes them less brittle. Remember, heat treat is one of the critical bottleneck resources in this particular plant. So what the folks in the goal did was they decided to stop running certain parts through heat treat, and that effectively raises the capacity of heat treat, because it raises the capacity of heat treat then to run parts that absolutely need to be heat treated. But what does that lack of heat treatment do then to work centers when they're running the parts that haven't been heat treated? Well, it means they have to run them slower, right? So again, if we look at those non-bottleneck resources that have to run slower, we look at them in isolation, we may say, well, you're making them less efficient. And technically that's correct, but that's okay because we're making the bottleneck, heat treat in this case, more efficient. We're essentially increasing the effective capacity at heat treat. Again, a lot of companies have trouble with subordination because it causes us to do things that make us uncomfortable. It causes us to do things that we're taught traditionally aren't right. Traditionally we think that maximum performance everywhere maximizes system performance, but this idea of subordination in the 5 focusing steps says, hey, that's not really true. The resource we need to maximize is the bottleneck. Therefore, non-bottleneck resources should be really focused on the bottleneck. Okay, let's move on to step 4. Step 4 is elevate. This one is pretty intuitive. We've at some point squeezed all the output we can out of our existing constraint resources, and at some point we're going to have to make the decision maybe to go out and actually get more of the resource. If they purchased more heat treat ovens in the goal, or they purchased another NCX10 machine. Those would be good examples of elevating. They didn't actually do that, but one thing they did, as you may recall, is they brought back some older machines that did the same job as the NCX10. That's a good example. Outsourcing is another good example. Both of those basically buy you more capacity at the constraints. And remember, the final step is to go back and repeat, because if you do enough of this good stuff, the constraint may actually shift to another resource in the company. Just when the folks in the plant figure out how to do the 5 focusing steps and it looks like everything is just going great, another crisis emerges. All of a sudden, jobs can't be final assembled because green tag parts are beginning to show up short. Recall that green tag parts are parts that don't go through a bottleneck, so Alex and the other folks expected that those parts would have no problem flowing through the plant, showing up at final assembly, and they'd probably be waiting a while for the red tag parts to show up. But as it turned out, after a while, that's not what was happening. They did a little bit of research, and they discovered that what was happening was that people in the goal were releasing extra work into the plant, ahead of schedule, in other words, in order to keep the non-bottleneck resources busy. You can see this picture down here in the bottom. Just to simplify things as much as we possibly can, we're just looking at 2 work centers here. The second work center clearly is the bottleneck. It's got a capacity of only 150 an hour. So the question that we need to ask ourselves is, how much should we try to get through work center 1? What level of utilization should we expect to have at work center 1? Well, if we can only get 150 units through work center 2, then we should only try to process 150 units at work center number 1 on average. So that would imply about a 75% utilization. If we strive for 100% utilization at work center 1, because we think that high utilization everywhere is good, what's going to happen? We keep completing 200 units every hour at work center 1, but we can only get 150 out of work center 2. Inventory is just going to build up, and that is basically what happened in the goal. In these chapters 24 and 25, you can see that they're swimming in inventory. So it's important to understand that to optimize the system, again, you need to optimize the bottleneck. As Jonah says in chapter 25, a system of local optimums is not an optimum system. If we try to optimize everywhere, chances are we won't actually optimize the system, and that's what they learned in chapters 24 and 25. In those chapters, Jonah makes the distinction between activating a resource and utilizing a resource. This is a little bit different from the traditional definition of utilization. Jonah would say that you're only utilizing a resource if you're using it to make money. So in other words, if we take work center 1 and we run it more than 150 units per hour, then we're just activating the resource 25% of the time. We're not actually utilizing it, because we're using it just to keep it busy, which he would call activating. As they noted in chapters 24 and 25, some models don't need to go through the constraint at all, but on those models, the constraint is the market. And that lesson becomes a little bit more apparent when the next problem rolls around and hits the plant. And that's the problem that eventually they start running the facility so well that they run out of backlog. In other words, they don't have enough orders to fulfill anymore. So what they do is pretty bold. They start quoting much shorter delivery lead times. And in order to facilitate that, they cut the sizes of all process batches at non-bottleneck work centers. That might seem a little bit counterintuitive. You might say, well, why don't they work faster? But really, cutting the batch sizes is a much more powerful way to have the effect that they want to have. And that becomes apparent if we think about the second bullet point here. We can think about the time that material spends in a system as setup time, queue time, process time, and wait time. The value is added in the process time. That's when you're actually processing the material, adding value to the material. If it's a service, it's when we're actually serving the customer. But that material undergoes other time. A batch of material, or a particular unit in a batch of material, is going to spend time waiting for a resource to be set up. Every unit in the batch would incur the same amount of setup time at each resource. And then once we run the first unit, the time that the second, third, fourth unit spend waiting for the units ahead of them to be processed is queue time. We all experience queue time when we wait in lines. Wait time is going to happen if we're in a situation where we've got several parts that have to be assembled together to make a finished good, and some of the parts are available, but some of the parts aren't available. The parts that are available, when they're waiting for the parts that aren't made yet, are incurring wait time. In other words, if we make stainless steel coffee mugs with plastic handles, and all the stainless steel parts are done, but they're waiting in final assembly for the plastic handles to show up, the time that the stainless steel parts are waiting around is wait time. Again, queue time is the time that a particular unit spends waiting for its turn to be processed while the other units in its batch are being processed. So, in other words, if there's 100 units in a batch, then the average unit has to wait for 49 units to be processed before it can be processed. And when those 49 units are being processed, it's incurring queue time. So if I cut my batch size, and my queue time is a function of my batch size, the size of the batch, then I'm going to cut my queue time. And that's basically what they did. It's interesting to point out that at first, doing that caused the efficiencies to decline because they were doing more setups for the same amount of output, and that made it look like a bad decision. So we started out talking about the goal, talking about the importance of performance measurement, and here once again, poor local performance measurement almost caused these guys to make a bad decision. They had the courage to go ahead and do what they knew needed to be done, and as it turns out, long term, cutting the batch sizes improves the flow of material through the plant and decreases idle time and has a good effect on efficiencies. But in the short term, they had to take a hit. I think one thing that's real important to understand here is that to decrease our overall lead time, we don't need to work faster. We don't need to hurry. We don't need to reduce process time. In other words, we can do some other smart things without having to decrease the time that we actually spend adding value to a unit. So I'd like to wrap up by talking just a little bit more about what a constraint is. Again, I use the term constraint and bottleneck interchangeably. Some people would say that a bottleneck is a physical resource and a constraint can be a physical resource and other things. But let's just make sure we understand that a constraint, like a bottleneck, is to put it fairly simply, a resource that prevents a system from making more money. It's the limiting resource on the system. Many times that's a physical resource. In the goal, that was the robots and the heat treat machine. A constraint can also be the market. Sometimes we have more capacity than we have market demand, and we saw that in chapter 28 of the goal. A constraint can also be a managerial policy or some type of policy that the business maintains. For example, demanding high utilizations on non-bottleneck work centers. If we stuck with that policy, that would create some pretty significant problems, as we saw in chapters 24 and chapters 25 of the book. A manufacturing organization might have a policy that they only ship full pallets of stuff to the warehouse because they want to save money on pallets, and that may indeed save money on pallets, but it may prevent other good things from happening. There may be late orders, and customers may be screaming for material. So that would be a policy that might prevent the organization from making as much money as it possibly can. An educational institution might have a policy of only offering classes when there's enough students to fill up a classroom, and that may make great use of classrooms, but that might get in the way of the institution's mission of educating and ultimately adding value and adding productivity to the community that it's supposed to serve. So many times organizations are not subject to physical constraints, they're actually subject to policy constraints. So that concludes our discussion of the goal. I hope it's apparent that the concepts that we've talked about are not only applicable to manufacturing, but they're applicable to lots of other situations. There's certainly many situations where we've got constraints to deal with, such as healthcare, where we have shortages of personnel, such as doctors and nurses, in airlines, and then other industries that use very expensive capital goods. Those capital goods, such as airplanes, are generally going to be the constraint. If we manage those systems with constraints effectively, we can maximize the overall output and productivity of those systems.